So, dear colleagues, we present to your attention a report on the topic Study of Low Cycle Fatigue of Specimens from Fine-Grained and Coarse-Grained Concept. The purpose of the work is to conduct experimental studies of fine-grained and coarse-grained concretes under low cycle loads and to establish the low cycle fatigue of the study's concretes. As a result of the impact of cycling loads, structures may experience a specific type of failure, where unlimited deformation growth occurs in the structural material under repeated loading, even when these loads do not exceed the ultimate one-time load. Thus, one of the priority tasks is calculating the strength of structures under low cycle loading is to determine the levels and numbers of repeated load cycles at which deformation stabilization occurs. During operation, building structures and their elements may encounter overloads, meaning that repeat cycling loads can exceed the calculated values. After a certain number of load cycles, such actions may cause significant plastic deformation in the structure, leading to a limiting state under the influence of repeated cycling loads. Low cycle fatigue. Various studies have shown that changes in the structure of concrete due to the size of the aggregates lead to the shifts in the levels of load corresponding to the lower and upper limits of microcrack formation. These studies found that coarse fraction as structure elements of concrete act as stress concretors, causing stress fields at the matrix aggregate interface where microcracks primarily found. Experimental research methodology. To study the low cycle fatigue of concrete more thoroughly, samples made of heavy concrete using traditional aggregates, two types of coarse-grained concretes and samples made of fine-grained concrete with sand as the only aggregate, were fabricated and tested in the research laboratory. The concrete samples were made with slag portrait sand. For sand concrete, the aggregate used was quartz sand with a fineness models of AIM 1.8 to 2.2. The sand was thoroughly washed from clay and sealed in parishes and dried. The grain compositions of the sand for the fine-grained and coarse-grained concrete samples of the first type is present in the table. For coarse-grained concrete samples of the second type, the fine aggregate was also quartz sand with characteristics determined in accordance with local standards. The fineness models of the sand was AIM 1.18 and its grain compositions is shown in table 2. Concrete mixtures were prepared under laboratory conditions. The dimensions of the prism samples were 4 times 4 times 16 centimeters for fine-grained concrete, 10 times 10 times 40 centimeters for coarse-grained concrete of the first type, 15 times 15 times 60 centimeters for coarse-grained concrete of the second type. The samples were cast in a horizontal molds and compared on a vibration table. Samples were demolded at the age of 28 days. Prism measuring 4 times 4 times 16 centimeters were tested under low-cycle compressive loads using a specially fabricated spring device. Prisms measuring 10 times 40 centimeters and 15 times 60 centimeters were tested under cycling loading on a hydraulic press. Before testing, the prisms were centered under a preload of 0.15 to 0.20 rub. Samples were loaded to a specific upper level at a constant stress rate, with increment steps of 10% of the expected failure load. At each load step, a hold period of 4 to 5 minutes was maintained to allow for the development of plastic deformation. The number of load cycles applied to the concrete prism samples during testing was not limited. The number of cycles was recorded until the samples failed. The tests were conducted on samples at significant ages, 410 to 536 days, fine-grained concrete, 143 to 178 days, coarse-grained concrete of the first type, 350 to 371 and 601 days, coarse-grained concrete of the second type. For a fixed lower load level of 0, the upper level of low-cycle loading was set as follows: 0.87 to 0.96 rub for fine-grained concrete, 0.82 to 0.95 rub for coarse-grained concrete of the first type, 0.78 to 0.88 rub for coarse-grained concrete of the second type. During experimental studies, the following were recorded: the upper level of low-cycle loading, the number of loading-unloading cycles until the samples failed. Result of experimental research. The test results of the prism subjected to low-cycle loads are presented in the table. For describing the low-cycle fatigue of the tested concrete prism, a fractional linear function in the form of the dependency eta size to n size was adopted formulas. From the diverse dependencies, it is evident that at their limiting values, they acquire physical meaning. Developments eta cycle 0.906, 0.841, and 0.747 correspond to the low-cycle fatigue limits for their respective types of concrete. The low-cycle fatigue of concrete obtained from dependency respected a hyperbolic curve in the coordinate axis, stress level, eta cycle number of loading cycle, and cycle, sustained by sample until failed. Maximum and residual values of longitudinal and transverse deformation increments of concrete were determined for the range of low cycling loads. Changes in longitudinal and transverse deformation of concrete are presented. Conclusions. The first one. The methodology for experimental studies of prism samples made of fine-grained and coarse-grained concrete under low-cycle loading has been presented. The second, Function is the form of the dependency, cycling load level, number of loading-unloading cycles until simple failure were obtained. The third, the low cycle fatigue limits of the tested concretes were established as at the cycle 0.906, 0.841, and 0.747 for fine-grained concrete, coarse-grained concrete of the first type, and coarse-grained concrete of the second type, respectively. The first one, hyperbolic curves in the coordinate axis, stress level, number of loading cycle, sustained by sample until failed were constructed. Thank you.